Welcome back to class. Today is an asynchronous lecture, so you're just going to be listening to this at whatever time you happen to be listening to this. Just one housekeeping note in terms of how the asynchronous lecture will work. There is not going to be a question portion today just because I can't be online 24 hours to accommodate whatever time you happen to log on. So I'm just going to finish up the chapter and then go straight into the exercise. The exercise just needs to be submitted by the end of the day, which is midnight. So just make sure you turn it in sometime before midnight, and then that will count for your participation score. Right now, we're working our way through Chapter 3, which is the Grossman model. In last class, we had a whole bunch of notation that was just intended to set up the model. And so you may be wondering, who cares about this? Or why are we learning all this notation, and what good does the model do us? And that's a good question. So as recall, the reason the Grossman model is helpful is because it gives us a framework for thinking about how to make a person as happy as possible when there are only two levers that influence happiness in this particular world. And these levers in the Grossman model, or we call them variables, are a person's health and a person's home good. So the reason all of this modeling is useful is because when we have a very simplified and rigid framework for thinking about how a person gets utility, then theoretically we can solve for the optimal levels of H and Z that a person would need to produce if they wanted to maximize their U or their utility. So in other words, there's probably particular values of H and Z where if you have those particular levels of health and home good, then that's kind of a sweet spot where you could generate the maximum level of utility that's possible. And the model lets us find that optimal combination of H and Z that would maximize utility. One note, I'm going to do everything today within the context of a particular day. So the time period is going to be one day. And if you're reading the textbook carefully, you'll notice that the textbook goes into kind of a multi-period framework. I think it's sufficient for you to just learn this in terms of a single time period. So I'm going to do the single time period maximization, and that's all I'm going to require of you for the class. If you're interested in how to extend this to a lifespan, read on in the textbook, but I won't be asking you any questions on the exam or in the exercise about the multi-period framework for the Grossman model. Okay, so what we're going to think about to start with is production possibilities frontiers. So in the Grossman model, you need to produce health and you need to produce home good to get utility. And one thing we can do is we can take a graph and we can put health on one axis and we can put home good on the other axis. And then we can plot the frontier of what is possible to produce in terms of different quantities of health and home good. And we think of what is possible in terms of what is possible given our limited amount of time and money, which are the two resources that we have to work with in the Grossman model. In economics, we call this frontier of what is possible to produce a PPF, or a production possibilities frontier. Just note that the name of the PPF is very descriptive. So each coordinate along a PPF gives a combination of values such that that combination is feasible to produce. But the PPF is the frontier of what is feasible to produce. So any point outside of the PPF corresponds to a combination that is not feasible to produce. Similarly, any coordinate or combination inside the PPF, it's definitely feasible to produce, but if you produce that combination of the two items, then you're not at the frontier of what is possible to kind of churn out if you tried to exhaust all your resources. As we talked about in the first chapter, health models just kind of break the rules in terms of everything that we're used to. So what I want you to think about is what a typical PPF looks like, and then I'm going to show you why we can't use that typical PPF here. So most professors, when they're teaching about a PPF, or particularly when they're teaching about a typical PPF, the story that they often tell is the story of a farmer who's trying to produce two crops. So maybe the crops are soybeans and corn. So the farmer's got some land and he's got some time, and these are the resources he has, just like in the Grossman model, you have time and money. And this farmer needs to figure out how many soybeans he'll produce and how many units of corn he'll produce, and he can kind of shift his resources between making soybeans and corn. And in the typical setup, we get a PPF that looks kind of like the second half of a rainbow, and we say that all the points along that curve are possible for the farmer to produce. What I want to do now is draw your attention to a particular dot that is on a standard PPF, and it's the dot that's at the top of the PPF, and I want you to think about what that dot means. So in the case of soybeans and corn, that dot would tell us that it is feasible for a farmer to take all of his resources, exhaust them all on soybean production, and then if he does that, he'll get the maximum yield of soybeans that is possible for him to farm. But as a result, that would cause him to not have any corn crop. So his corn yield would be 0 because he would have taken all of his resources and pushed it towards soybean production. Okay, now let's flip the script and think about this in terms of the two things that we're trying to produce in the Grossman model, which are not soybeans and corn, but they are health and home good. We're going to put health along the horizontal axis, and we're going to put home good along the vertical axis. And for starters, let's just draw the PPF like we would if we didn't know any better, and then let's think about what the same dot that we've been talking about would mean in the context of health and home good. Okay, that dot would tell us that it is possible for a person to get the maximum yield of fun stuff or home good in their life, and at the same time have health of 0. Okay, something about that should just not sit right with you. As you move left along the graph, what that corresponds to is a person's level of health falling. So if you get to the point where health is 0, that means the person has no health left at all, so they're basically dead. So that dot that's up on the screen, that would be a dot that would exist if it was possible for a person to have absolutely 0 health at all, and then to simultaneously have the maximum yield of fun things in their life. And that's just not realistic, because in order to have fun things in your life, you have to have some level of health. For one, you need money to have fun things in your life so that you can buy stuff. And for you to have money, you need to have a job. But if you're next to dead, then you can't feasibly hold down a job. So it's not plausible to make the assumption that a person can have 0 health at all and then at a level of 0 health have maximum fun in their life. So PPF shaped this way is just not realistic in the context of the Grossman model. And instead, the health and home good PPF in the Grossman model is more realistically rainbow shaped. So think about a rainbow shaped PPF. If you're on the first half of the rainbow, then that means a person's level of health is somewhat low. They're just not super healthy. But as you start to nudge your way right, then the person's health increases. And on the first half of the rainbow, that person's home good is also increasing as you move right. So that actually is realistic. If you have a person who starts out with a very low level of health and then they become just a little bit healthier, then there are big returns to that health increase. For example, if you can just go to work for 1 hour per day, then you finally have a little bit of money for you to buy fun things like movie tickets. So when you get just a little bit of health and you can go to work, well, then that means that 1, your health is increased, but 2, your home good is also increased because now you can buy the movie ticket. And that occurs when you start moving rightward from a low level of health. So for the first half of the rainbow, it is definitely feasible for a person, it's feasible and it happens that a person both gets healthier and at the same time they also get more home good. Okay, now let's think about the second half of the rainbow. Notably, the second half corresponds to higher levels of health. And along this portion of the rainbow, if you want to get more health, that's certainly possible, but to move further right, you're going to have to give up some home good. And for reasons that I'm going to show you in a minute, it's very realistic that the world could operate in this way. For example, suppose you have someone who's kind of a gym rat who spends like 8 hours a day at the gym. If that person wants to get even healthier, then what is he going to have to do? Well, he's going to have to spend like 9 hours a day at the gym. So he makes this decision to spend an extra hour at the gym per day. And what happens is that his health will go up In other words, he will slide right along the PPF. But now that he's spending this extra hour at the gym, he also has to take away time from playing with his kids. So that's a home good thing because it's just an enjoyable thing. And so for this kind of shift in his activities, where he's spending this 9th hour at the gym, well, he does get healthier, but his Z also falls. So note that this trade-off between more H and more Z only happens on the second half of the rainbow, where people are somewhat healthy to begin with. Okay, so what I'm going to do now is I'm going to just kind of walk you through the rainbow. There are different coordinates that I have labeled in your notes. In your own notes, take notes of what I'm saying in terms of what these different coordinates tell you about kind of the defining features of people who reside along these different locations of the PPF. All right, so we're going to start at the bottom of the rainbow, at point A. Suppose you have a person who's residing at point A. That point is the leftmost point along the PPF. That means it is not feasible for the person to be any less healthy. They're basically just hanging on for life. What is also true about that person is that they have zero home good, or in other words, they just have zero fun stuff in their life. Now, if you look at this person's time constraint, what you would see is that if you are as unhealthy as you can possibly be, then that's basically like the person spending 24 hours being sick. And so if they use all of their 24 hours in the category of TS, that means that their working time and their playing time and their time that they could be spending doing health improving activities, all of those categories have to be 0. So the working time, the playing time, and the time spent doing health improving activities, these are what comprise productive time. So at point A, a person has 0 productive time because all of his hours have gone into the category of TS, and TS is the one activity that is not included in productive time. And since there's no productive time, of course the person won't have any Z because they don't have any capacity to produce Z. Okay, let's make the story a little bit happier. Suppose a person slides from point A to point B. Think about point B for a minute. Point B is on the upward sloping portion of the PPF. How would we characterize a person in that situation? Well, in that situation, a person has a small amount of health. Their sick time is not 0, so they have some time available for productive activities. That means they can feasibly produce some Z, or some home good. So with the little bit of health that they have, they can spend some time going on a walk, or they can spend some time at the movies. And those are all productive activities. And so what is true about point B is that as a person kind of moves up the rainbow and they get healthier from a low baseline level of health, they're simultaneously getting healthier, so their H is increasing, and they're also getting some home good in their life, so their Z is also increasing. One way you can think about this mathematically is in terms of just a concrete example. So think of a super unhealthy and out of shape person. Maybe they decide, well, right now I'm not going to the gym at all, and so I'm going to decide to go to the gym 1 hour every day. As a result of that decision, their TH would go up by 1 unit. If they're on the first half of the rainbow, then there are enormously large returns to investing in health. And so maybe as a result of that 1 extra hour in the gym, the person's sick time falls by 2 hours per day. Okay, the time constraint has to hold. So if they spend 1 extra hour in the gym and that results in 2 fewer hours being sick per day, well, that means that on net, they freed up an extra hour in their day that they can either spend working, or they can spend it playing, or they could even do something else that's health improving. And as a result, in total, there's going to be a 2-unit increase in their productive time from just spending that 1 extra hour per day at the gym. Okay, suppose a person keeps creeping up the rainbow and they reach point C. At point C, the person's level of health has improved to the point where it's pretty decent. And at this level of health, 1 extra hour spent on a health-related activity, or in the modeling, this is the variable TH, that extra hour spent on a health-related activity will yield exactly 1 fewer hour being sick. So this is equivalent to 1 extra hour of productive time in total, and productive time has only gone up by 1 hour because you have gone to the gym or you've done some health improving activity for 1 more hour. So if we go back to the concrete example and we pull out the time constraint and we think about this person who's at this medium level of health and they spend 1 extra hour at the gym, then for this person, this will lower their sick time by exactly 1 hour. Again, the time constraint has to hold. So all of the increase and decrease in hours spent across different activities is just going to immediately wash. So the extra hour spent at the gym is instantaneously offset by the 1 less hour spent being sick. So in total, the productive time of this person has gone up by just 1 hour. Okay, now suppose the person slides down to point D. At this point, they're starting to kind of become a gym rat. So their level of health is somewhat high. And at this point, they'll have to start giving up some fun things in their life if they want to accommodate a more rigorous gym schedule. So let's pull out the time constraint and try to demonstrate this. So for a person who's on the downward sloping portion of the rainbow, to begin with, they're not spending much time being sick because they're pretty healthy at baseline. So 1 extra hour in the gym would lower their sick time, so it would make them a little bit healthier. But they don't have that much sick time to begin with, so it would lower their sick time by less than 1 hour. Again, the time constraint has to hold. So if they're spending an extra hour at the gym, but their sick time is only falling by half an hour, then that means they have to pull half an hour out of some other activity to accommodate, again, their more rigorous gym schedule. So they're either going to have to spend 1 half hour less at work or half an hour less playing. So their productive time in total is going to increase by only half an hour, although they're spending a full extra hour at the gym. Okay, last stop on the rainbow, point E. The first thing to know about a person who resides at point E is that the person is at the highest level of health that is possible. So in other words, the person's like a complete gym rat. They're as healthy as they can humanly be, but in order to be as healthy as they can humanly be, that means they have to take all their resources, which in the Grossman model are all their hours and all their dollars, and they have to completely exhaust them in order to increase their health. So while they're as healthy as possible, suggesting their sick time is probably pretty close to 0, they're probably going to be spending almost 24 hours per day at the gym. It's like if you want to get any healthier, then you have to spend more time in the gym, which means you'll have to pull more time out of work and or pull more time out of playing hours, and you're just piling all of the hours and all the resources that you have into the TH category. And so at some point, presumably, you're just going to run out of time to work and play, or at least do the minimal levels of those things. And so at that point, your home good is just going to be 0, although you're quite healthy. Again, what we're trying to do with this model is to figure out the particular combination of H and Z that is optimal if the goal of the model is to make a person as happy as possible. Side note, the goal of the model is not necessarily to make a person as healthy as possible. The goal is to maximize their utility. So what we're going to do is we're going to treat the PPF as a sort of aggregate constraint that incorporates the time constraint and the budget constraint. So another way of thinking about the PPF is that it's the frontier of all the different H and Z combinations that are feasible for a person to produce, given the time and money constraints that they have. And conveniently, if we treat the PPF as an aggregate constraint, then we can maximize utility subject to this aggregate constraint, the PPF. Okay, one thing to note is that although a person can never produce an H-Z combination that is beyond what is feasible, and the PPF is the frontier of what is feasible, there are going to be some combinations of H and Z along the PPF that we can rule out as optimal in terms of maximizing the person's utility. In other words, certain coordinates along the PPF will never be the solution to the Grossman model. For example, consider the combination that I've denoted on the screen. That corresponds to a certain level of Z and a certain level of H that a person could feasibly produce. The question is, would that level of H and Z be a combination that would make a person as happy as possible? The answer is no, and hopefully it's clear why. The reason it's no is because if you slide up the rainbow a little bit to get to another feasible combination, then that second combination on the PPF is such that the person has more Z and they also have more H than they did at the initial combination. So while both of the combinations or coordinates would be feasible for a person to produce, if the goal of the person is to maximize your utility, and utility is a function of H and Z, well then the coordinate that gives you more of H and more of Z is clearly preferable. So you can just rule out the lower coordinate as being optimal. And you can kind of follow this pattern all the way up the rainbow to rule out all of the H and Z coordinates on the first half of the rainbow. In other words, none of those particular coordinates would ever be the winner in the Grossman model in terms of those levels of production of H and Z, making a person as happy as possible. So what we're going to do is we're going to kind of rule out the first half of the rainbow as being an effective constraint, because the person is not bound to those coordinates. They have other options, and those coordinates will never win in terms of making the person as happy as possible. So when we cancel out the clearly never optimal region of the PPF, that just gives us the effective constraint, and the effective constraint is going to be the second half of the PPF. In this region, the effective constraint region, if you move between any two coordinates in this region, then what will happen is that if your health increases, your home good will decrease. Conversely, if your home good increases, your health will decrease. And so on the surface, it's not immediately clear which coordinate would be best to maximize a person's utility, because there's some trade-off in terms of what you're producing. Either you're producing more H or you're producing more Z. You're not simultaneously producing more of both. There's a trade-off. All right, again, we want to figure out which HZ among the feasible coordinates is the best or would generate the most utility. So to do this, we're going to impose indifference curves. And if you have not taken intermediate micro, I'll give you a real quick catch-up. Indifference curves are curves that reflect fixed levels of utility. So anytime you move to an indifference curve that is higher than another one, that just reflects moving to a higher fixed level of utility. So what we're going to do is we're going to think about the second half of the PPF rainbow as our effective constraint, and we're going to take indifference curves and sort of push them out as far as possible until we exceed what is feasible, or until we start crossing the PPF. And what will happen is that when we've pushed them out as far as possible, one indifference curve will kind of catch, or it will be tangent to the constraint. And wherever that tangency happens, that will reveal the optimal HZ coordinate that a person would need to produce if they wanted to maximize their utility. On the screen, I have the effective constraint bolded, and then I have the indifference curves just kind of imposed upon this. So again, we just take the indifference curves and kind of keep pushing them out and out until they can't go any further than what is feasible, or until they reach the frontier of what is feasible to produce. And at that point, there will be a tangency that corresponds to a particular level of H and a particular level of Z. Okay, that H star and Z star where the tangency happens is going to be the solution to the Grossman model. So it is the level of H and the level of Z that a person would want to produce to make them as happy as possible. So in other words, if you plug the H star, whatever that number is, into the utility function, and if you plug the Z star, whatever that number is, into the utility function, then out will spit a utility level that is higher than any other utility level that you would get had you plugged in other values of H and Z. Okay, you can take a deep breath. That's the end of the Grossman model. So I'm going to take a step back into reality. Models sometimes get kind of theoretical, so I'm going to just kind of drive this home in terms of what's real about the world. As I mentioned before, models are kind of like maps, and in maps and in models, we strip out some of the details of the world just to simplify things. And sometimes we even make assumptions that aren't entirely true. So on maps, highways are often drawn in red, but in real life, highways aren't actually red. So we kind of like change reality in the map or in the model just to kind of clarify things. So what I'm going to have you do is think about one assumption of the Grossman model from a very high level, and then I'm going to show you some science or give you a real-life example of why that doesn't quite line up with reality. Okay, the assumption of the Grossman model that I want you to think about is the assumption that investing more time in health will always lead to improved health. So if you look at the health production function, if you spend more time on health-improving activities, the model would say that that improves your health. Okay, so for the sake of storytelling and trying to make this remotely interesting, I'm going to read to you a Wall Street Journal article, so you get a little bit of storytelling here. And what this article demonstrates is that this assumption of the Grossman model that if you spend more time doing health-improving activities, or in other words, if you spend more time exercising, then great, that will always increase your health. According to this article, there's reason to believe that that actually may be a faulty assumption of the model. So the name of this article is The Potential Cardiac Dangers of Extreme Exercise, and you can just follow along or listen as I read a portion of it to you. The article says, a new study finds that exercise that is extreme in either volume or intensity may be associated with high levels of atherosclerosis in the coronary arteries. The study, presented in August at a meeting of the European Society of Cardiology, studied 169 veteran competitive endurance athletes against a control group of 171 relatively sedentary subjects. Compared to the control group, the study found lower levels of coronary artery calcium in athletes who ran fewer than 35 miles a week or cycled fewer than 150 kilometers a week. But athletes who ran or cycled beyond that threshold were found to harbor higher levels of coronary artery calcium than did the control group. The study, conducted by British physicians, is certain to intensify debate over one of the most controversial questions in modern medicine. Can people exercise too much? By all accounts, exercise lowers blood pressure, helps preserve coronary artery integrity, lengthens lifespans, and otherwise promotes physical and mental health. Exercise is medicine, say public health officials. But unlike other medications, which is generally prescribed in scientifically determined doses, exercise typically receives a blanket more is better recommendation. Most health benefits occur with at least 150 minutes a week of moderate intensity physical activity, such as brisk walking, says the U.S. exercise guideline. It adds additional benefits occur with more physical activity. Now, a small but growing number of studies suggest that the benefits of exercise may diminish or even disappear beyond a point. Some evidence suggests that the longevity benefits of endurance exercise may disappear for some extreme athletes. Other evidence shows higher than expected coronary artery calcification in such athletes. And then I'm going to skip to the bottom of the article. Other studies, along with the sudden deaths of famous runners such as Micah True, give other cardiologists pause. Chronic excessive strenuous exercise can exact a toll on the durability of the cardiovascular system, on how well the pump holds up through the decades, says James O'Keefe, a Kansas City cardiologist. Most cardiologists are awaiting more research. We know that there is some point where we reach diminishing returns from exercise, says Clyde W. Yancey, a Northwestern University cardiologist. But it remains very unclear whether exercise at some point poses danger. Okay, as a final thing for the day, I want to show you one figure, and then we'll go into the exercise. This figure I pulled directly from the research paper that was referenced in the Wall Street Journal article, and I'm going to orient you real quick to the figure, and then I'm going to help explain how even this figure demonstrates that the assumption of the Grossman model that more time spent doing health-improving things is better, well, that assumption probably isn't exactly true. Okay, so in the figure, the horizontal axis is daily physical activity duration in minutes. So along the horizontal axis, they're just plotting how long did somebody exercise. And then the vertical axis is all-cause mortality reduction. We like when mortality is reduced, so higher values are better. It's like you're even less likely to die as you move up along the graph. Okay, I'm going to highlight for simplicity one subset of people in the study, and these are the people who exercise vigorously, and they have the orange dotted curve in this figure. So the orange dotted curve shows you the relationship between daily physical activity duration and your likelihood of dying among people who are exercising very vigorously. So these are like people who are sprinting. Okay, the first thing to note is that the dashed line kind of tapers off at 50 minutes. And this should be intuitive if you're kind of actually thinking about this, because if we're considering sprinters, well, you can't sprint for hours on end. And even after 50 minutes, it's really hard to keep on sprinting. And so there's just not data beyond 50 minutes, likely because people aren't sprinting longer than 50 minutes. However, that doesn't mean that there's not a relationship between mortality and exercise duration after 50 minutes. It exists, it's just not observed in the data. So let's just suppose, hypothetically, that the researchers took the people in their experiment and they just forced them to sprint longer than 50 minutes just to figure out what the relationship is for those durations. Well, if we extrapolate based on the curvature of the orange dashed line, then what's probably going to be the case is that that curve is going to start bending down. And that's not a stretch of the imagination at all to presume that that's what would happen, because that would mean that if you take somebody and you make them sprint 60 minutes and then 70 minutes and then 80 minutes and then 90 minutes, then it starts hurting them such that it's not just that their mortality reduction flatlines, it's like they become more likely to die because you're just pushing them so hard. So if that is the case, then that would be at odds with the Grossman model, because the Grossman model says more is better. If you increase the person's TH, then their H will increase, whereas based on the Wall Street Journal article and then this figure from the research paper, it's probably the case that if you really push people to exercise beyond certain thresholds so that the duration is really high, then at some point that's going to have a detrimental effect. Okay, the last thing I want to just mention about this super quickly is that there's two ways that we can see from the figure that Grossman actually got it right. So the first way that Grossman got it right is he made the assumption that health is a capital good. In other words, health is the only thing in his model that carries over from one time period to the next. Note that the dependent variable in the figure is mortality. Mortality doesn't happen the day, hopefully it doesn't happen the day you go running. So the figure is saying that running today influences mortality tomorrow. That's consistent with Grossman's assumption that the time that I spend on health today affects my health, but then my health yesterday affects my health today. So there's kind of carryover effect when it comes to health. The second way Grossman got it right is he assumed diminishing returns to productive time. So in other words, he said, you know, if you have less and less sick time, or conversely, if your productive time gets larger and larger and larger, that is going to be better in terms of your health, but kind of the bang for the buck that you get in terms of your health improvements is going to kind of start to dissipate a little bit. And the way we see that is the dashed orange line is not a straight line, it's a curve. And so if you move from 0 minutes of exercise to 10 minutes of exercise, that leads to a pretty big reduction in your mortality. Whereas if you move from 40 minutes to 50 minutes, the reduction in your mortality is quite a bit smaller. So there's definitely diminishing returns. Okay, that's the end of lesson. If you are still listening to me, well done. Okay, the exercise today is going to be to think about where people with particular characteristics would be residing along the PPF, and then how that's affecting their productive time. So I'm going to give you two scenarios, and then I just want you to fill in the blanks. In the first blank, I want you to respond with either increase or decrease. In the second blank, I want you to respond with a number. And then in the last blank, I want you to respond with either upward sloping portion, downward sloping portion, or peak, where you're thinking about location on a PPF. Okay, scenario number one that I want you to think about is suppose there's a man named John, and John chooses to increase the time he spends on health by 1 hour per day, and this causes the time he spends being sick to fall by 2 hours per day. Okay, so again, tell me whether his productive time is going up or down and by how much, and then what portion of the PPF he's on. Scenario number two is now assume we're thinking about a woman named Mary, and Mary chooses to decrease the time she spends on health by 3 hours per day. And this causes the time she spends being sick to increase by 1 hour per day. So again, for Mary, will her productive time increase or decrease, and by how much? And then what portion of the PPF is she on? So make sure you have, in total, 6 responses since there's 6 blanks. Get it submitted by midnight, and then you'll be good to go.